I wanted to talk about a momentary button before we get into the use of our momentary button in our circuit. So here we have a momentary button. Sometimes this is referred to as a tactile button. You can really feel the clicking when you do press this. It's momentary, meaning that when I press it, I can close the contact, and as soon as I release it, the contact has been released. So it's only momentarily connected. The momentary button has 4 separate posts. 2 of the posts are connected electrically, and we can see that in the top right corner. Those 2 posts that are both bending in on the same side, those are electrically connected. If I were to do a continuity check, I would have continuity between those 2 posts. The switch is between, that can be seen on the bottom right picture. So how the posts bend in towards each other, that is where this switch occurs. So we have continuity across the top right one, and we have a switch across the bottom right. We'll be using the momentary switch in the circuit that we created in the previous lab. Set up your board so that it is similar to the previous lab. The momentary switch, the type that we're using, this tactile button, is designed this way to be able to connect or fit into a breadboard. We can see here on the picture on the left with the blue background, that is the direction that we should be placing the momentary switch on the breadboard. It's a good idea to try to put it into the middle of the columns of the breadboard so that we can do measuring and testing on both sides. Once you have the momentary switch in place, take a multimeter and measure the continuity without pressing the button. You should get an OL. If you have continuity, then you have the switch in the wrong position, and then you need to rotate it 90 degrees and place it back into the breadboard. You should have continuity when you depress the momentary button. Go ahead and measure the continuity while depressing the button. Here you can see that I have 7.4 ohms. Yours may be slightly different than this, but this indicates that the switch is closing when I press the button. Here I've used a metal rod to depress the button so that you can see where my multimeter leads are. Notice that I put my red meter lead on the other side of the button, but still maintain continuity when pressing the button. Alright, we need to ensure that we have the latest code, so I'm going to open up the terminal and do a change directory, and we are in the desktop, and then my Pi projects, and then ATTC 3260. Okay, now that I've navigated to here, I can issue the command git pull. That will give me the latest repository from GitHub. Okay, now we're ready to take a look at the code in our IDE. So I'm going to use Thony for this. Just open up Thony and then do File, Open. And we want to open up Lab 5, and then we want to open up Lab5.1.0. Alright, this code should look fairly familiar. We've used it in the previous example. The difference is that we are changing GPIO.both to GPIO.falling. GPIO.both, it is looking for any change that occurs in the input signal. GPIO falling is a change that goes from high to low, and then we'll see in the next code we use GPIO.rising, which is a change looking for a change from low to high. In our example, pressing the button and receiving information that a button has been pressed is really the critical thing, but I want you to recognize that the computer is looking in this instance simply for a change from a high state to a low state. The other change is just increasing the bounce time. Remember, the bounce time is essentially how long in microseconds that we should wait before we try to determine whether or not another signal has been pressed. If you have this number fairly low, when I press a button, it may register the button being pressed multiple times. We will see some strange interaction when we're depressing the button in this instance, and that just has to do with the limitations of the Raspberry Pi. But for the most part, we're going to see what we expect. All right, let's go back to the terminal, and we're going to run this code. So we're going to issue the command Python, and then we're running Lab5.1.0. If needed, go ahead and pause the video and get your board set up so that it matches this one. It's very similar to what we had done before. I'm running this white wire from GPIO 17, and I'm placing it on the top end of the button. The red and black wires are positioned just ready to be able to be connected to the switches. Everything else should remain pretty close to what you had set up before. If you put your red meter lead on the GPIO 17 pin and your black meter lead on ground, you should get a 3.3 volts or somewhere close to that. That would indicate that you are running the Python program and that you have a pull-up resistor set as the input for GPIO 17. Notice that nothing is connected to the button except for the GPIO input wire. Next, what we're going to do is we will provide a ground for the GPIO 17 so that we can close the circuit and indicate that the button has been pressed. So I've moved the ground wire to connect to the bottom end of the tactile button or momentary button. And now when I press that button, you should see that the multimeter reading goes down to 0. We've closed the switch, and now current is flowing through that part of the circuit. We're dropping our voltage at the pull-up resistor, and we're indicating to the Raspberry Pi that the button has been pressed. You should also see a print statement in your terminal that indicates that the button has been pressed. Because of the limitations of the Raspberry Pi, it's possible that when you press the button, it might print the statement a couple of times. That doesn't necessarily mean that you've written something wrong in your coding or that your wiring is incorrect. It has a little bit to do with the frequency of measurements that are occurring based on the limitations of the Raspberry Pi. What we should see, though, is that when we change the state from a high at 3.3 to a low at 0, that the CPU recognizes that change, and that is happening. That's a falling edge. Let's go ahead and open up our 5.1.1 code. In the 5.1.1 code, we are using a pulled down resistor, and the big change that we'll see here is that we're now using a GPIO rising. That is our edge detection. We're looking for a change from a low state to a high state. All right, go to the terminal and run the Python script for 5.1.1, and this is the electrical connections that we'll be making. So the only real difference from the previous one is we're now putting 3.3 volts in the button position, so that when the button is depressed, we'll apply 3.3 volts to GPIO 17. When we depress the button, we'll see that change in voltage. It'll go from 0 volts to 3.3. So it's going from a low state to a high state, and the edge detection rising should catch that state change and indicate that the button has been depressed by way of the print statement that we see in the terminal. So there wasn't really much difference. We did introduce the button, a momentary button, in the form of a tactile switch, and we looked at the change to edge detection. In the next lesson, we'll look at a momentary button that acts a little bit differently than this, but I wanted to make sure that you were aware of how the button worked and its interaction in the circuit.